Well, this lecture is going over the Unit 4 final exam project. Specifically, I'm going to give you a quick overview of what this looks like, and then I'm also going to go over the very first page on this. First of all, you guys are going to, I'm going to go ahead and share my screen. By the way, um, if you hear voices in the background and whatnot, that is because I am out of town right now with my family, and that is a whole bunch of kids and my wife in the background. So this right here is the Unit 4 final project. This is the, uh, more specifically, the file that I'm looking at right now is the example file. And in the example file, I have a whole bunch of different um, tabs on the bottom. You'll see right here in the very first tab, I've got the Excel formulas tab. If you scroll down, you'll see a whole bunch of different Excel formulas that you can test out that will help you to be able to do what it is that you need to do. Also, there's a page just on assumption testing. And then there's a decision tree, just like always, because I mean, who doesn't love decision trees? And then we're going to a reference file or a reference page. And I have a reference page that kind of just gives you information for each of the tests. So I've got single reference, independent. This is for running an independent samples test, and then paired, and then we've got the goodness of fit for equal proportions and goodness of fit for unequal proportions, is the one at the very end, right there. And then I also have an example of what your final project should look like. And so there is a single example, independent example, paired example, goodness of fit, equal proportions, and goodness of fit, unequal proportions. And in this lecture right now, specifically, we are going to go over the single sample the single sample page, so that way you can see how to complete this. Um, so looking right here, like I said, we have a reference page, and I have all of the questions right here that you are going to be completing as by yourself, and then also at the bottom you're going to be completing this as a group. Then also I have information to the right hand side of, hey, this is how you do this, so you can see how to do it. And then right here, this is what you're actually completing. So for each topic, you're going to be completing your own. Right now, I just, like I said, redid this entire thing to try to make it a little bit more streamlined. And so we're going to go through this, and I'm going to show you how to complete this. And this right here is very much so, sorry, I'm also on a touchpad, and it's not as easy as working with a mouse. And that's what happens when you try to do things on the road. Um, but what's that called? When you go through this, you're going to um, yeah, just follow along with me, and you'll see exactly how to complete it, and we'll go from there. So, looking back at this, each of you are going to have each group has their own data set. And so you might have Spotify songs, you might have UFO data, you might have I think I've got like 20 different data sets that you guys can choose from. And so you might have a different data set, but what we're going over here specifically, which I have a page for you that says, hey, this is exactly what your group is going over. But what we're going over here is I have Hot Wheels cars. And I don't know how many of you guys grew up with Hot Wheels cars at all. Uh, I actually didn't. I had very few Hot Wheels cars. Maybe I'm just trying to make up for lost time here by playing with them now. But I have this Hot Wheels set that actually gives you the top times, the speed, so on and so forth. And so we're going to be working with that data, and we're going to be going through that. So I raced, I think, 30 cars, and I raced each car multiple times to give us more data points. And so we have that information here now. And I'll, when I get a minute, probably this afternoon, I will upload a video that shows you exactly the experiment that I did, so you can kind of understand, hey, we're taking the top times, we have the different designers, we have a whole bunch of different data on all of these, all this Hot Wheels information, and it's just kind of fun to try to, look at, hey, there's data everywhere. So first, what we have here is we have the example, and let's see here. I'm going to change this question really quick. What we have here is Hot Wheels wants to know, they want somebody uh, to design some fast cars for them. Because the students, or the kids, sorry, the kids are getting upset because they're like, hey, you know what? These cars aren't fast enough. These cars are going slow. They're getting these cool designs, but these cars are going slow. Okay, so Hot Wheels wants to, let's see here, Hot Wheels wants to choose a designer who makes fast cars to design the new line of cars. Okay. Uh, can I be 90% confident that, let's see here. So I chose one designer. Can I be 90% confident that, and his name is Mason uh, Chung, 90% confident that Mason Chung designs cars that uh, go faster than the population average. Um, Population average speed. And the way that this Hot Wheels track works is they say, okay, based on the size of the car that you are racing, you are proportionately, which I think it's like a 1 to 64 ratio. Or something to that effect. So, based on the size of car that you're racing, we are going to say, oh, it's traveling X miles per hour. And so, Mason Chung, he made cars that go 119 miles an hour, 62 miles per hour, 108, 129, 58, and 59 miles per hour. And the average of all designers is 79.14 miles per hour with a standard deviation of 24.25, and his standard deviation is 33. More specifically, Mason Chung, his responsibility, from what I can tell, is he designs the Batman cars. And so all the Batman cars come from Mason Chung, and all the rest of the cars come from everyone else. But when we say the population, this includes Mason's cars as well as everyone else's cars. And so we're going to come right over here, and we're going to go through this. First of all, what is a dependent variable? Okay, well, the dependent variable is really, what is it that we're actually measuring? There is something that's dependent on something else. Okay, more specifically, we have the speed of the cars, and they are dependent on who the designer is. Okay, one is Mason Chung, and the other one is all designers, including Mason. And I'm going to see if I can get something really quick. Let's see here. I'm going to try to grab, let's see here, final project. There is a really decent chance that I do not have the actual data here, which would be very unfortunate. Let's see here, hot. We'll see. Oh, we do have it. Oh, we don't have it. So I have an actual sheet. It's just not here. It's at home, and unfortunately, I'm about 350 miles away from my home. So we're not going to be able to see it. But we have a whole bunch of different information on all of these cars, and we have, like I said, 30 some odd different cars. We have the designer, we have how much they weigh, we have serial numbers, we have the colors, so on and so forth. And so I've got all of that information. and I just don't have it here, unfortunately, because I saved it in the wrong place, or maybe I didn't save it at all when I was at home. Um, and so right now I'm on my laptop, so I'll have to grab that later. And yeah, so let's pull this up because I do have all the data that we're analyzing at least. So Hot Wheels, let's see here, final project. So we have the dependent variable, then we have the designer because the car speed is dependent on who the designer is. Now the next question is what type of data is the independent variable? So this right here, designer, is it nominal or null interval or ratio? In this particular situation, it's nominal, and it should be nominal, or it could possibly be ordinal, but it really should be nominal. Or another thing that you could say is that it's categorical, right? Because you have different categories. You and the different categories are it's either designed by Mason or it's designed by somebody else. And then what type of data is or sorry, what are you examining or comparing? And so we're going to very specifically look at a single reference. And this is what I want you to do is if you're like, oh, what is it that I'm supposed to be doing? You come in here and you say, okay, what are you examining or comparing? And you look under the purpose right here. Let me get myself out of the way. There we go. Look under the purpose, use of the test, and adapt it to the written answer. So what we're doing is we're coming over here and we're saying, oh, we've got the purposes of the test. And you're going to choose one of these three, and same thing for independent, paired, so on and so forth. You choose one of the purposes and you adapt it for what it is that you're doing. Okay, and so coming right here is what are you examining or comparing? We are comparing the speeds of a sample of Mason's cars to the population to determine if differences exist. So you'll see I took this to determine if or to compare a sample to a population to determine if differences exist. Next, what is the tail of the test? And here's a little hint for you: different, two tail, greater than, right tail, less than, left tail. So just, if it's different, you do two tail, greater than, do right tail, less than, left tail. And so right here, specifically, or I put upper or right. So you can put upper or right. The reason why is because you look at this and you want to know Mason's cars, do they go faster? Well, we're comparing Mason to the population and always do it in that order. So the uh, Mason's cars compared to the population, that is an upper tail test because we are saying, hey, we believe that Mason's cars are going to go faster than sorry, I'm also sitting on the ground right now and it's a little uncomfortable. So we believe that Mason's cars are going to go faster. Next, you write the null and alternative hypothesis. The null hypothesis is saying we believe that there's no difference between Mason's cars and the population. And so we're saying that the mean of Mason's cars is going to be less than or equal to the population mean. And so if you come right over here, you'll see, okay, we've got the population mean and we've got the population standard deviation. And you'll notice we've got the population mean and the population standard deviation right there. And then so then we also have the mean of Mason's cars is greater than 79.15 is the alternative hypothesis. Next, what is the level of significance? The level of significance is 0.1. And notice the reason why is, can I be 90% confident that Mason's cars go faster than the population average speed? So that's why we have 0.1. Next, what is a test statistic? The reason why it's Z. So the question is it Z or is it T? If you have just a really simple, if you have the population standard deviation, use a z-score. If you only have a sample standard deviation, use the t-score. So here we have a population standard deviation, so we're going to use a z-score. Next, what are the degrees of freedom? The degrees of freedom, which really don't matter here because we have the population standard deviation, but the degrees of freedom is n minus 1, which once again, if you want to check, you're like, oh, how do you do this again? And everything that I'm saying right here, I have it all written out. Okay, so you have all of this information right here. And let's see here. Single sample. And then coming down here, what are the critical values? The critical values, there's two ways to get this. First of all, let's go ahead and open up. Let's see. You should have this in your file somewhere, the critical values diagram. Let's see here. So I made this super cool critical values diagram for you that you can download under the printable resources. And this is a two-tailed test, or sorry, this is a one-tail upper tail test, and it wants me to sign in, unfortunately. And so this is a one-tail upper tail test. And let's see if I can just move this out of the way and avoid signing in right now. And you'll see we have a one-tail upper tail test uh, with an alpha of 0.1. So the Z critical is 1.282. And if it was a two-tailed test, it would be plus or minus 1.645. So what I'm going to do is I'm going to come right back here and I'm going to put 1.282. I'm going to minimize that and 1.282. And then there's also, if you come right here, there's other ways to do it, but these are kind of wonky. You've got to really make sure that you know what you're doing. So the critical values test or the critical values diagram that I made for you there works really well. Okay. Are there any assumptions violated? Um, so yes, yes and no. So what are assumptions? There's a whole lesson on assumptions, so make sure that you look at those assumptions. But for each of the tests, they each have their own different assumptions, or essentially, hey, we need to make sure that this is true about the data, or else the information or the insight that we're getting cannot be reliable. So we've got these four assumptions right here, and you need to say, okay, assumption one dependent variable that is measured at the continuous level. So remember the dependent variable. We've got this dependent variable here. Is it continuous? Yes, it is continuous. You're like, well, it looks like it's discrete because there's no decimal points. You're right. There is no decimal points, but speed, all that it is rounded. These are all rounded decimal points. We just don't see it. Why? Because the program that I have doesn't give me that. So, but this is continuous and the dependent variable is continuous. Next, we need to look at data. Are the observations independent? Is this observation independent of this observation, independent of this, independent of this, independent of this, independent of this? And the answer is yes. These are all independent. These are all each individual observed speeds. So each of those are independent of each other. Are there no significant outliers? Good question. Well, in order to determine if there's significant outliers, what we need to do is we need to highlight and we need to say insert, and we need to, let's see here, make a box and whisker plot. Then when you make a box and whisker plot, you will see there are no outliers, which you can also just drag this box and whisker plot down to the bottom. There's a place for you to put the box and whisker plot over here. So just be aware of that. So you can put the box and whisker plot down there, and we'll go over that in a minute. So, but I'm going to just delete this for right now. So there's no significant outliers. And last but definitely not least, should the dependent variable be approximately normally distributed? Now, here's a problem with that. It is very difficult to see whether or not this is normally distributed with just 6 data points. So, is it normally distributed? Well, it's not normally distributed. And so with the data that you have, it's going to be much easier to tell. But the things that you can do in order to determine if it's normally distributed is look at the skewness and kurtosis. and I'll show you how to do that. So in order to look at the skewness and kurtosis, you can either use Excel formulas for skewness and kurtosis, or um, we can run the, hold on, just, okay. Sorry, I'm only working on one screen right now as well, which means that I've got to move stuff around. Okay, let's see here. So we're going to do data, and we are going to click on the data analysis tool. And I don't know why it's not letting me look at the data analysis tool. There we go. Data analysis tool, and we're going to click on descriptive statistics and click OK. Okay, and the input range. So right here, we've got this input range, and we're going to delete that. Let's see here. And we're going to say, okay, I want you to give me all of this information right here, everything on speed. And I have a label in the first row, and then the output range, and make sure that it's grouped by columns like this. Output range. So I'm going to say, okay, I want it to go right here. Your area should be blank. Okay, and I want it to go right there. And then I want the summary statistics and the confidence level for the mean, and I want a 90% confidence level for the mean, and I'm going to press OK. And there's existing data. The reason why there's existing data is because I already did it once, but I'm going to click OK. So confidence level for the mean, so on and so forth, and yeah. So, which by the way, I accidentally did everything at a 95% confidence level earlier. That's why I'm going to be changing stuff as we go throughout this in just a minute. But what is this Unison Kurtosis? You'll notice right here the Unison Kurtosis. As long as the skewness is less than 1, you're good to go. And as long as the kurtosis is less than 3, you're good to go. And so for both of these, they don't violate the assumptions of normality, but they don't, because there's only 6 data points, it's really not that great either. So that's why what I did here, are there any assumptions violated? What I wrote in there is because the sample size is small, it's difficult to determine if the data is distributed normally, but for all intents and purposes, it's fine for what we're doing. Next, what is the calculated value of the test statistic? Okay, the calculated value of the test statistic is what we've been doing. All that we're doing is we are taking the sampling error and we're dividing it by the standard error. So what I did is I took the sampling error right here, which sampling error, remember, is just the sample mean minus the population mean. So that's the sampling error right there. And then the standard error is the standard deviation, or more specifically for what we're doing, the population standard deviation, divided by the square root of the number of observations in the sample. And so that's 9.9 is the standard error. And so we take the sampling error divided by the standard error, and that gives us a z-score of 1.012. And so what I did is I put that right here. And then on the right-hand side, this is where I want you guys to put, hey, I actually know what I'm talking about, giving me some, hey, this is information showing you that I actually know what I'm doing. So the sampling error of 10.012 or 10.02 divided by the standard error of 9.9 equals 1.012. The standard error is very large because the sample size is so small. And so you'll notice right there, that's all the information that we just did. And then once again, there is information over here in case you're like, hey, how do I do this again? So we have, what is the test statistic? Let's see here. Okay, the sampling error divided by standard error. For lower or left tail test, it's always negative. Well, it should be negative. Make sure that it's negative, if it is. If the if the sample is less than the population, it should be negative. Um, the let's see here. The critical value, this really should say, for the critical values for a left-tailed test, it's always negative. And for the calculated values, it should be negative, but it's not always negative because sometimes you're just straight up wrong. Okay, so next, what is the probability of observing a sample value as extreme as or more extreme than the value? So the way that we do this is we use this fun little formula, which you can go to the Z table if you want to. I don't really like using the Z table for multiple reasons. The biggest reason is because it's not nearly as accurate. Okay, but for this, what we're doing is norm.s.dist. And so I did norm.s.dist, and then I put in the z value. So this is the z value, and then I put cumulative. So what this does is this tells me what is the probability of getting anything less than the z value that I got here. So everything to the left of that z value. So that's actually quite a bit. So what that's going to do, whoops, sorry, that's going to give me 0.84423. Okay, so this is the probability of getting anything less than what I got, assuming that that there is no difference between Mason and everyone else. Or just Mason and the entire population. But what I need is what is the probability of getting Mason's speed or greater, or Mason's score or more extreme. So what I'm going to do is, in order to get the complement to that, is I'm going to do 1 minus norm.s.dist. Okay, so I'm going to do that. And then if you have a two-tailed test, you multiply that by 2. So more specifically, let's do this. I'm going to copy and paste. Control C. Let's put this into single reference. So for norm.s.dist, let's do this. Left tail. And I'm going to copy this. Control C. Oops. Don't you hate it when that happens? And then let's do right tail. One minus norm.s.dist. And then two tail is going to be either 2 multiplied by norm.s.dist, or it's going to be, Control C, 2 multiplied by 1 minus. And it's going to be whichever one is less than 1, because probability can never be greater than 1. So it's going to be one of these if you're dealing with what's it called? If you're dealing with z values. Okay, if you're dealing with t values, you've got a two tail, you've got a left tail, and you've got a right tail. I don't know why they make it so much easier for t values. It is what it is. Next, your decision. And then once again, I put the probability of observing an average of 6 track times with a mean of 89 or 6 speeds. It should say speeds with a mean of 89 or more extreme is 15.58%. Okay. And then next, the question is what is your decision? We fail to reject the null hypothesis, or we fail to reject the idea that there is a difference between the two, and it's 1.282, because the z value of 1.012 is less extreme than the critical value of 1.282. There we go. Okay. Then next, what is the margin of error? So this is really simple. The reason why it's so simple is because the margin of error is literally right here. It says confidence level 90%, and this is literally your margin of error. All that you've got to do is Control C and put this right here. And so with a margin of error, and like I said, I accidentally did it for 95%. So I'm going to change it. Control C, put it right here. Okay, and if you wanted to, so this is the actual mean speed of cars designed by Mason Chung is 89.167 with a margin of error of 27.16. And you could do, if you wanted to, the margin of error by actually doing what we did in the previous unit with multiplying the z-score of 1.282 by the standard error. But we don't have to do that. Yeah, so that's the margin of error. Yeah. So next we are looking at the effect size. And the effect size is 0.143. And the way that we get this is we come back over here and you'll see, okay, single reference. And we are coming right down here, and the effect size is the absolute value of the mean of sample one minus the population mean divided by the standard deviation. So what I did is I came over here and I said, okay, I took the difference, or essentially the sampling error, and so I took the sampling error divided by the standard deviation. So the sampling error, once again, is 10.02 divided by the population standard deviation, which is 24.25, which if you have the population standard deviation, always use the population standard deviation. And so that gives me 0.14. And coming right back here, you'll notice that I've got a nice little Cohen's D. This is called a Cohen's D effect size. And it says, okay, how do you interpret this? Okay, so 0.02, 0.05, 0.08, it's either a small, medium, or large effect size. And so a small effect size is like, you know what, I can kind of see it, but not really. I need a really big sample size in order to be able to actually see the difference. Medium is like, okay, I need like a medium sample size. We can kind of see it, it's kind of there. And large is, well, you can see it. It's like, hey, the difference between the height of a basketball player and the height of a gymnast, it's really easy to see with just a few people. It's a big difference. And so that's what we have right here is 0.4. So it's somewhere between small and medium. So we're going to come right back here and it says, okay, this is a small to medium effect size indicating that a larger sample is needed. In order to see a difference between cars designed to see a difference in speeds. Speeds between cars designed by Mason Chung and all Hot Wheels cars. So that is the effect size. Next, we're coming down here and it says, okay, what is it that you're going to interpret from these results? First of all, what was run? And you're literally just kind of giving me like a narrative of what it is that you just did. Pretty straightforward. So a single sample hypothesis test was run, and just you click on these. A single was conducted, and then let's go down. What was the purpose? Which literally I'm just kind of copying from up above. What is the purpose? And sorry, to compare the speeds of Mason's cars to the population to determine if differences existed. And so that's pretty much the exact same thing that I put right here. And then what was the result? The results indicated that we could not conclude that there was a difference in car speeds between the cars designed by Mason and all Hot Wheels cars. Then what is the p-value of the result? The probability of observing the average of 6 track times with a mean of this of 89.167 or more extreme is 0.1558, or there's a 15% chance of getting that or something more extreme. Then a larger sample size is needed. Given the insight, give insight about possible factors influencing this. And then we put a larger sample size is needed to determine if differences truly exist. You could also put it uh, the sampling error of 10 point. Let's see here. What did I? Oh, 10.0202 indicates that there could possibly be a difference, but it is not possible to determine right now with the information we have. In other words, we just don't have a large enough sample size. Next, the present results cannot be used to indicate, excuse me, let's see here. How should the results be used in regards to the research question, which once again, the research question is at the very top. It says, can I be 90% confident that Mason Strong's designs go faster? And so what I wrote in here is the present results cannot be used. Let me zoom in a little bit. The present results cannot be used to indicate cars designed by Mason Chung are faster than the average of all cars. A larger sample size is needed to determine if a difference truly exists. And so that's this information down here. Definitely work together with your group to put all this together. And then coming down here, you'll see, okay, we've got this fun little box and whisker plot. And, this is just going back to unit 1. I want you to be able to make this box and whisker plot, which remember, if you click on this box and whisker plot, you're like, oh, these super cool values are right here. Yes, those values are definitely right there, and you can use those, but they're not going to be in yours. And the reason why is because you need to click on the chart. And if you double click on it, it should give you, okay, add chart element, data labels, and I put my data labels to the left. And you can play around with this and just make it better. Make sure that you've got a title for it. And then right here we have 129 for the highest value. That is not an outlier. If you have outliers, they're going to be up here or down there with little dots. And when it says describe your outliers, it says describe the outliers above. You just put something like there are no. Oops, and it's not working. There are no outliers above. And or if you have a whole bunch, you say, okay, there are 20 outliers between this value and this value, or there's 2 outliers and it's at this value and this value. And then same thing, down here, describe the outliers below, do the same thing. There are this many outliers between this and this. And then the max value that is not an outlier, 129. Q3, you can literally just read it from the graph, 121.5. And then the median is 85, which is right there. You'll see it on that line. The mean is a dot, that X right there, and you'll see the value of the mean. If you zoom in, we'll be able to see it. It's 89.1667. So that's what I put right there, 89.1667. And then Q1, you'll see Q1 right down here, and then the lowest value that is not an outlier is right down there. And if you do the actual calculations by hand, they might be a little bit different. That's because there's a couple different ways to actually calculate Q1, Q3, yeah, it's more very specifically Q1 and Q3. So just be aware of that. And last but not least, make a histogram for the sample. In order to make a histogram for this sample, literally all that you've got to do is highlight it, highlight the sample, and do insert. And we are going to do histogram, and you just do histogram, and then put in a title, and then you say uh, distribution of car speeds, or whatever it is that you have. All right, so that is what you're doing for the final project for the very first topic. I'm going to do the rest of them later, so just be checking back. Also, right now, I only have the one done for this. I only have the example done for the single sample example. So just keep checking back. I will have all these done very shortly, um, as soon as I can. I just yeah, just keep checking back. And But they will definitely be done before it is that you need to complete your work. Cool. I think that's all we got for now.